You ever send a photo and have it just appear on your friend's phone in a split second? It feels like magic, right? But it's actually some seriously clever engineering. Today, we're going to pull back the curtain on how these massive image files get shrunk down to sizes that can zip across the internet in the blink of an eye.
We've all been there. You upload a beautiful, crisp photo, but what shows up on the screen is, well, let's just say it's a little crunchy and pixelated. That distortion, it's actually a clue to the fascinating process we're about to dive into.
So what's the deal? The answer is image compression. It's the art of shrinking a file by getting rid of information that, honestly, your eyes won't even notice is missing. And let me tell you, the story behind how this all works is a fantastic journey of clever trade-offs and constant innovation.
All right, so to get this, our story has to start way back in 1979 with a surprisingly simple but really powerful idea for shrinking images.
It's called block truncation coding, or BTC for short. And the core idea? It's actually pretty simple. If the whole picture is just too complex, why not break it down into smaller, more manageable pieces?
So first things first, the algorithm basically lays a grid over the image, chopping it up into these little 4x4 pixel squares. All those numbers you see, each one represents a pixel's brightness. And just like that, instead of one giant problem, we've got a whole bunch of tiny ones to solve.
Okay, now for each one of those little blocks, the algorithm does something really smart. It calculates the average brightness. Then, for every single pixel, it asks a super simple question. Are you brighter or are you darker than that average? If it's brighter, boom, it becomes a 1. If it's darker, it becomes a 0. And just like that, 16 complex pixel values are transformed into a simple 16-bit map. Pretty neat, right?
And now for the final step, where it all comes together. The algorithm reconstructs the block using just 2 colors. That's it. One for all the zeros and one for all the ones. Now, is it a perfect copy of the original? Nope. But it's incredibly close. And here's the kicker. It uses way less data. We've just traded a little bit of perfection for a huge gain in efficiency.
Now this was a fantastic start, but of course, engineers pretty quickly realized they could make this whole process a lot smarter. It was time for the first big leap forward.
I mean, think about it. An image isn't uniform, right? You might have a super detailed area right next to a huge patch of a single color, like a blue sky or a white wall. The original BTC method treated all of those areas exactly the same way.
And you know, that's just not very efficient. Why use a tiny 4x4 block for a large area of flat color? It's like trying to color a giant poster with a super fine-tipped pen. You'd want a big brush for the large areas, and you'd save that fine-tip pen for the details.
So the next innovation did exactly that. It's called Quad-Tree Segmented BTC, or QTS-BTC, and it introduced a much more dynamic approach. It basically examines a block and determines if it's simple or complex. Here's how it works. The algorithm starts with a large block. If it's simple enough, like a piece of the sky, it stops right there. Done. But if it's complex, it divides that square into 4 smaller ones and checks each of those. It keeps dividing until it reaches the necessary level of detail, using the right brush for each part of the image.
This adaptive approach was a total game changer. But the quest for the perfect pixel never stops. So now, let's look at 2 cutting-edge paths that take efficiency even further.
First up, we have a clever data trick that's a bit like rounding numbers to save space. It's called bit shaving.
So, a standard color value is stored using 8 bits. Bit shaving essentially asks, what if we only store the first 6 or 7 bits and just assume the last few bits are 0? Now this slightly changes the color value, say from 215 down to 212, but it's a change so incredibly small your eye can't even see it. And in return, we save precious bits on every single color value we store.
Okay, the second path. This one addresses a fundamental limitation of that quad-tree method. It was smart, but it could only ever work with one shape. That quad-tree method can only divide things into 4 equal squares. But what if the object in your picture isn't a square? Well, the next evolution, KD-tree segmentation, or KTS-BTC, breaks free from this constraint by using rectangles of all different shapes and sizes.
I mean, just look at the difference here. On the left, you see those rigid squares from the quad tree method. But on the right, you've got the flexible rectangles of the KD tree. By creating long, skinny rectangles or tall, thin ones, the algorithm can trace the actual shapes in an image much more efficiently. It wastes way less space.
So these are all very clever ideas. But the big question is, do they actually make a difference? Let's look at the data.
This table here compares the bit rate, which is just the number of bits it takes to store each pixel, so lower is better. The original method, AMBTC, took 6 bits per pixel. The smarter Quadtree method cut that almost in half. But look at IQTS-BTC. That's the one with bit shaving. It reduces the file size even further, achieving over a 53% reduction from the original. That is a huge win.
But what about quality, right? Are we sacrificing how good the image looks for these smaller file sizes? This chart shows something called PSNR, which is really just a technical way to measure image quality. All you need to know is a higher number means better quality. And as you can see, the quality difference between the Quadtree tree and the more efficient K-tree method is basically nothing. It's almost non-existent. We're getting smaller files with virtually the same visual quality.
And that's really the crucial point here. This isn't about some single magic bullet. The entire history of image compression is a story of smart people finding clever new ways to make trade-offs, trading a tiny bit of quality you'll never notice for a significant gain in efficiency you definitely will.
You know, from breaking images into blocks, to making those blocks smarter, to shaving off bits and breaking free from the square, each step has been a brilliant piece of engineering. And it really leaves you wondering, as our images get bigger and our data needs grow, what clever trick are they going to think of next?